Welcome to the fascinating world of endocrinology. Imagine your body is a massive, bustling city with billions of cellular inhabitants who constantly need to communicate with one another. To keep everything running smoothly, the city uses different types of messengers, depending on the urgency and nature of the message. Today, we are going to explore these messengers, called hormones, and understand how they are classified, manufactured, and mathematically balanced in your blood. Let us start by defining what these messengers actually are. Hormones are chemical messengers secreted by endocrine glands directly into the bloodstream. They travel through the watery blood to regulate the activity of distant target cells. Think of them as the body's internal postal service. Some messages are like quick text messages, some are like detailed emails, and others are like heavy physical packages requiring special transport vehicles. Understanding this communication system is the very first step to mastering how our bodies maintain perfect balance, known as homeostasis, throughout our entire lives. Now that we know what hormones do, let us look at how they are built. We classify hormones into three major chemical groups. First, we have peptide or protein hormones, which are made of chains of amino acids and are water-soluble, meaning they float freely in the blood. Second, we have steroid hormones. These are derived from a lipid called cholesterol, making them fat-soluble, so they require special carrier proteins to travel. Finally, amine hormones are tiny molecules derived from a single amino acid, usually tyrosine, and can act like either peptides or steroids. Moving deeper into the cell, let us explore how these different classes are actually manufactured. Peptide hormones are synthesized just like any other protein in your body. The process starts with DNA transcription in the nucleus, followed by translation on the ribosomes to form a large, inactive precursor called a pre-prohormone. This precursor is then chopped down and refined in the endoplasmic reticulum and Golgi apparatus until it becomes the final active hormone. Because they are water-soluble, these finished peptide hormones are safely stored in cellular vesicles until the body needs them. In contrast to peptides, let us see how steroid hormones are produced. Steroid hormones are not coded by DNA directly. Instead, they are synthesized on demand in the smooth endoplasmic reticulum and mitochondria by enzymes that modify cholesterol step by step. This is a crucial difference. Because steroids are fat-soluble, they cannot be stored in vesicles. If the cell tried to store them, the hormones would simply diffuse right out of the lipid cell membrane as soon as they were made. Therefore, the body must manufacture them exactly when they are needed. To visualize what we just discussed, let us look at this diagram, comparing the cellular synthesis of the three hormone classes. On the left, you can see the peptide hormone pathway, starting from DNA in the nucleus, moving to the rough endoplasmic reticulum, then the Golgi, and finally being stored in a vesicle. In the middle, the steroid hormone pathway shows cholesterol being modified in the mitochondria and smooth endoplasmic reticulum, immediately diffusing through the cell membrane. On the right, the amine hormone pathway shows tyrosine derivatives being packaged into vesicles. Having seen how hormones are made, you might be wondering why we care so much about their chemical class. This classification is incredibly important in real-world medicine because it dictates exactly how we can treat patients. For example, insulin is a peptide hormone. If swallowed, it would be completely destroyed by stomach acid, which is why diabetic patients must inject it. Conversely, birth control pills contain steroid hormones. Because they're fat-soluble, they easily survive the digestive tract and can be absorbed through the gut, allowing them to be taken orally. Beyond just biology, let us shift our perspective to see endocrinology as a dynamic mathematical balance. The concentration of any hormone in the blood at a given time depends entirely on a continuous tug of war. On one side, we have the rate at which the hormone is being synthesized and secreted. On the other side, we have the rate at which it is being cleared or destroyed by the liver and kidneys. Endocrinologists represent this balance using a differential equation that tracks the change in hormone concentration over time, allowing them to predict patient outcomes. Building on that idea of balance, let us look at the formula for a patient's hormone levels when their body is in a stable, steady state. The formula states that the steady state concentration, denoted by H in brackets, equals the synthesis rate S divided by the clearance rate constant K. The synthesis rate S is measured in mass per volume per time, representing how fast the gland works. The clearance constant K represents the fraction of hormone removed per minute. If the synthesis rate increases, the blood concentration will rise, whereas if the clearance rate increases, the concentration will drop. Let us apply this formula to a concrete example. We are given a healthy patient whose thyroid gland synthesizes a hormone at a constant rate S of 20 micrograms per liter per hour. The patient's liver and kidneys clear this hormone with a clearance rate constant K of 0.05 per hour. We are asked to find the steady state concentration. We choose our steady state formula because the hormone levels are perfectly stable. We substitute 20 for S and 0.05 for K. Dividing these gives us a final concentration of 400 micrograms per liter, representing perfect homeostasis. Now that we have successfully used the steady state formula, let us understand exactly where it comes from mathematically. We start with the fundamental mass balance differential equation, which states that the rate of change of hormone concentration over time equals the synthesis rate minus the clearance rate. To find the steady state, we must realize that the hormone concentration is no longer changing over time. Therefore, the mathematical reasoning dictates that we set the derivative, the rate of change, exactly equal to 0. This establishes the condition for perfect balance in the body. Continuing from our previous step, we have set the rate of change to 0, giving us the equation 0 equals S minus K times H. This tells us that the synthesis term must be perfectly equal to the clearance term. To isolate the concentration variable, we move the clearance term to the other side of the equation. Finally, we divide by the clearance constant K. This simple algebraic rearrangement yields our final result. The steady state concentration is directly proportional to the synthesis rate and inversely proportional to the clearance rate. We have proven our formula. With our formula proven, let us look at a pathological scenario involving the exact same patient. Unfortunately, this patient has developed a benign tumor, drastically increasing their synthesis rate to 60 micrograms per liter per hour. The clearance rate remains unchanged at 0.05. We need to calculate the new steady-state concentration to understand the disease severity. We use the same formula, substituting the new elevated synthesis rate of 60. Dividing by 0.05 gives a final answer of 1,200 micrograms per liter. Physically, this means the patient's blood is flooded with excess hormone, causing severe clinical symptoms. We have covered a lot of ground today, So let us reinforce the most important ideas. First, we categorize hormones into peptides, steroids, and amines, which dictates whether they are built from amino acids or cholesterol. Second, this chemical structure determines whether they are stored in vesicles or synthesized on demand. Finally, the actual concentration of these hormones in the blood is a delicate mathematical balance between cellular synthesis and bodily clearance. You have now mastered the foundational bedrock of endocrinology, giving you the tools to understand both healthy human physiology and complex endocrine diseases.